All right, so what we're going to be talking about today is we're going to be starting into Unit 5, which is all about linear momentum. So we're going to be focusing today on the idea of what is momentum, and then how is momentum conserved in some situations. So momentum and conservation of momentum. So let's talk a little bit about what momentum actually is. Momentum, which is represented by the variable p, is defined as the product of an object's mass and its velocity. So if you think of what that means, we get a very simple equation where p, which is, as you can see, a vector quantity, you could tell by the arrow on top of it, is equal to mass times velocity. So if something has a lot of momentum, it could either have a lot of mass or it can have a lot of velocity, or it could have both. So notice that depends on both. As I said, momentum is a vector, and the units for momentum are kilograms times a meter per second. There is no special unit for momentum, so we just use these units of kilograms times a meter per second. One important to note about momentum and the vector quantity is that the direction of momentum is always in the same direction of the velocity. So when we talk about momentum, we could talk about momentum's direction, and it will always be the same direction in which the object is moving. So the same direction as the velocity. A force is required to change the momentum of an object. Whether, and as you guys can see on my notes, I'm not going to go back and change this right now. I spelled the wrong whether it increases, decreases, or changes the direction of the momentum vector. So a force has to be applied to an object to change its momentum. And we could do it by several different ways. We could increase the momentum, which might be increasing the velocity. We could decrease it, or we could change the direction of the momentum vector. When we think about Newton's law, Newton's second law was actually originally stated within the terms of momentum. And this is his original law, was that the force is due to the change in momentum over a period of time. And there is a derivative, and you guys can see if you can do this on your own, where you could actually replace this and you could actually solve for force equals mass times acceleration. So these two ideas are related. Let's talk a little bit about collisions. When objects collide and exert forces, on each other. So when two things collide, there is a force that is exerting from object 1 to object 2 and vice versa. According to Newton's third law, the forces are equal in magnitude and opposite in direction. So remember, we had Newton's third law, which says for every action, there's an equal and opposite reaction. So when two objects collide, the force of object 1 on object 2 is going to be in equal and opposite magnitude of object 2 on object 1. So we get this equation right here. So again, the force on, in this case, B on A is equal to the negative of the force of A on B. These forces are applied during an equal time interval. And when we talk about that equal time interval, what we're talking about is the time in which they collide. So how that is the time interval that we're talking about. So the change in momentum is also equal and opposite to the opposite for object A and B. So if we go back to this equation that we have right here, and we say that time is the same, so pretend like time is 1, then force and momentum are the same. So if we think about that, we can get this idea where the momentum, or the change in momentum of A, is equal to the negative change in momentum of B. And so you can again think, well, what is changing? Change is final minus initial. So here is the final momentum of object A minus the initial momentum of object B is equal to the negative of the final momentum of object B minus the initial momentum of object B. So this is actually Newton's third law of situations, may involve not only velocity changes, but mass changes as well. So I want you to think about what might be an example of a mass change in a collision. So when might you actually have a mass change in a collision? Well, you could have a couple different things. Think about the idea of when, say, a football player is tackled. Once they collide, they kind of move together afterwards. So we're talking about like one object becoming two. So you have kind of like a shared mass. So the mass changes afterwards. The other thing that you could think of is, let's say an asteroid strikes a planet. Well, some of the mass of either the asteroid or the planet changes afterwards because the asteroid hopefully broke up. So you can see that the mass changes with there too. We have many other examples. We could talk about car collisions where the mass might change after the collision. What about a velocity change? So that might be a little bit more intuitive to think about, but maybe when two cars collide, their velocity changes. When you have a bullet shooting from a gun, and we'll see an example of that. What we have is that's actually a recoil, but you have a different velocity afterwards. So there are many different cases in which we can think about collisions. So what is a conservation momentum? And maybe you're already intuitively thinking about this, but if the system is isolated, remember what we talked about, the idea of isolated, that means that no energy or matter is entering or leaving. The total momentum of all the objects in the system before the collision will exactly equal the total momentum of all the objects after the collision. So this is the law of conservation of momentum, and it's represented. We could rearrange this equation. So if we rearrange and we distribute our negative, and then we rearrange the equation, we can get this. So notice that what I have here is our initial A and B, our final A and B. And then if you go ahead and put in mass and velocity in this equation for our conservation, or for the idea of momentum, you get the before and after collision. So this is the law of conservation of momentum. So we're going to look at a couple different collision problems. So isolated collision problems usually involve nearly frictionless situations, and that's because friction is usually a force from outside the system. So usually it's not within our system, so we don't talk about it. Objects may fly apart, collide and stick together, or bounce off of each other. So many different ways in which a collision could happen. So we're going to look at this example problem. We have a 1,875 kilogram car going 23 meters per second, and it strikes a 1,025 kilogram car going 17 meters per second in the opposite direction. The two cars stick together. What is the velocity of the two-car system after the collision? And we want to ignore our friction. So let's go ahead and switch screens and look at that example. Okay, so let's go ahead and look at our first problem. In order to understand this problem, I am going to do an amazing artistic representation of our two cars. So let's say here is one car, and it has some wheels, and it is moving this way. We'll call this car A. And moving in the opposite direction, maybe this is a truck. Let's have a truck. So moving in the opposite direction is car B. So let's think about before. So before the collision, I'm going to label my drawing so that we know what we're dealing with. Car A has a mass of A is going to equal 1,875 kilograms. And it has a velocity. Let's have this way be positive and this way be negative so that we can make sure that we identify our velocity vector correctly. So this is going to be a positive 23 meters per second. And then we're going to have MB is going to be 1,025 kilograms. And velocity of car B is going to be negative 17 meters per second. Now, after what happens is that these two cars move as one. So they actually collide, and let's see if I can, let's say here's a collision point. So this is A, and it collides with B. So here they are, they're collide. And so now we want to know, what is their velocity. So velocity of A and B. And the velocity of A and B is going to be the same because they are moving together as one. We can also still identify our masses. So mass of car A is still 1,875 kilograms. Mass of car B, whoops, you guys can't see that, sorry. Mass of car B is 1,025 kilograms. Okay, so let's go ahead and look at our equation for this problem. So we have, and I'm going to kind of write this out in kind of longhand so that we have all the information that we need. Let me move this up. We have MA initial times VA initial plus MBI initial, velocity B initial is going to equal MA final VA final plus MB final VB final. Okay, now I can kind of break this apart. Now, if we know that these two velocities are the same, so we know that VA final is going to equal VB final. What we can do is that we could just call that the final velocity. So if I do that and I pull that out, I could actually get this equation. I can get MA final plus MB final times, we'll say just velocity final. Because again, those two are moving at the same speed. And then let's just go ahead and do this, AVAI plus MVI VBI. Okay. So we could also, since we're just trying to find this, we can go ahead and divide both sides by our masses. And then we could just plug things in and solve for, we can solve for our final velocity. So that gets canceled out, and I will get that my final velocity is going to be equal to this. So let's go ahead and plug things in to our equation. So mass of A is 1,875 kilograms times its velocity plus 1,025 kilograms times its velocity, which is negative. Don't forget that negative because that is important, divided by the mass of the two added together. Okay, so that is my work. So let's go ahead and plug this into our calculator. I got 18,075 times 23. I'm going to add that to 1,025 times a negative 17. Don't forget that negative. And then I'm going to divide that by these two masses added together. And I get my final velocity to be 8.86 meters per second. And notice that's going to be going in this, let me go up. It's going to be going in this direction. So it's going to be going in the positive direction. And hopefully that kind of makes sense. Because if you think about what car had the most momentum, car A had the most momentum because not only did it have the higher velocity, but also had a much higher mass. So when it collides, The momentum is going to be, when they collide and go as one, the momentum conserved is still going to be in the positive direction because this car not only was going slower, but had a lower mass. So again, just looking at our work, my answer is 8.86 meters per second in the positive direction. Now we'll just go ahead and put a little positive there just to make sure. Let's look at this example as well. So we have a system and we have, it looks like some parts of a train, and we have part A and part B. And we want to know what must be true about mass of A and mass of B. So what it's really kind of asking is possibly what are those masses? So let's go ahead and talk about what we can figure out about the masses of these two objects. All right, so let's go ahead and think about the problem with the train cars. So we have, I'm going to do this. We have two train cars. We have A, and it has a velocity of 32 meters per second. And we have train car B, and it currently has a velocity of 0 meters per second. What happens is that A collides into B, and then they start moving together because they become linked. If you guys think about like the little hitches that hold the trains together. So then they move, and together they have a velocity of 16 meters per second. And so what we want to know is what can be said about the masses of trains A and B. So let's think about this in terms of law of conservation of momentum. So let's go ahead and write down our law of conservation of momentum. Now, what I'm going to do is I'm going to treat this system right here as a system together. So we're going to call this just our final system. So if I were to think about this, I have the mass of train A initial times the velocity of train A initial plus the mass of train B initial times the velocity of train B initial is going to be equal to the mass final times the velocity final, because again, they're moving together. Well, let's go ahead and plug in some of the things that we know. So we know that we'll say mass of A, and really, we don't necessarily need to say that it is mass A. I am going to break this apart and say that this is mass A plus mass B. So we know that we're talking about the combined masses of those trains. And it's going to have a velocity. We know what its velocity is. It's 32 meters per second. Plus mass B times that velocity, which we know is 0 meters per second, is going to equal MA plus MB. And we were told that this velocity is 16 meters per second. So this equation actually goes to 0 since it's not moving. It has no momentum. And what we end up getting, our units cancel out. So if I were to simplify this, what we end up getting is 32 MA, so we'll just call that MA, is equal to 16 MA plus MB. I'm going to distribute the 16, so 32 MA is equal to 16 MA plus MB. And if I were to get my MAs on the same side, I'm going to subtract 16 from both sides. So this actually says 16 MA is equal to, whoops, I forgot to put 16 here, 16 MB. Well, what does this tell us? What does this relationship tell us? This tells us that the mass of train A is equal to the mass of train B. So that is what we can say based off the scenario that we had, is that the masses of the two train cars were the same. We don't know what they were. This 16 doesn't tell us really anything. It just tells us that they are the same. So the mass of train A is equal to the mass of train B. All right, recoil problems. So recoil is very similar to collision, but there is something slightly different that we want to make sure that we take into consideration. So objects can not only collide, but they can fly apart, and that's what we call recoil. So an object that breaks apart, throwing pieces or components outwards, will also conserve momentum. Examples of this include radioactive decay, so when a particle is ejected from an atom, a bullet and gun system, rocket propulsion, and astronaut jetpacks. So these are all examples of recoil problems, and what we are thinking about is that it is one system and then it breaks apart into two different. So generally, the initial system velocity is 0, but an object such as a large atom may be moving initially before separation. So for example, in the gun scenario, if we were talking about a gun and a bullet and you shoot a gun, the initial velocity of the system would be 0, and then the velocity of the gun and the bullet, then there is a velocity for the gun and the bullet afterwards. So if we take that consideration and we say that our initial velocity is 0, and we plug that into our conservation of momentum, what we end up getting is that the momentum of A final is equal to the negative of the momentum of B final. And then again, plugging in the variables for momentum, we will get that equation. But remember, that is only if your initial velocity is 0. So here we have this problem that is going to be similar to a recoil problem. Helga and Sven are wearing ice skates and are standing on an icy pond. Helga has a mass of 52.2 kilograms and Sven has a mass of 70.8 kilograms. Helga pushes off Sven and moves to the right 2.13 meters per second. What is Sven's velocity? So what you want to think about is that initially they are not moving, and then they break up into two. So Helga goes one way and Sven goes the other way. And so now they both have different velocities, and they have different velocities mainly because they have different masses. So let's go ahead and look at this problem. Okay, so let's think next about our problem of Sven and Helga. So they start off as one. So here they are. Let's say they're holding hands. They're stick figures because that's all I can draw. So what happens is that they start off as one, and then they push off of each other and they move in opposite directions. So this is a recoil problem. One of the important things that we were told is that their initial velocity was 0 meters per second. So if their initial velocity was 0 meters per second, we could use kind of our little shortcut that we saw on the slide. So what we can do, let's go ahead and identify. Let's go ahead and identify Sven as being in the positive direction and Helga being in the negative direction, although it really does not matter. So we're going to have mass of Sven times the final velocity of Sven is equal to the negative mass of Helga times the velocity of Helga, the final velocity of Helga. So we want to know, we know what their masses are. We know what Helga's velocity was. So we're looking for Sven's velocity. So we're going to go ahead and divide both sides by the mass of Sven. And we get our equations. Let's go ahead and plug in our variables. Velocity of Sven final is going to be equal to negative, don't forget that negative, 52.2 kilograms. That's the mass of Helga, times her velocity, which is 2.13 meters per second divided by 70.8 meters. Excuse me, kilograms. That's his mass, not meters per second. So we get that. Notice that our kilograms cancel out and we're left with meters per second. And we are then told that the final velocity of Sven is negative 1.57 meters per second. You know what? I misspoke earlier when I said let's identify who is going in what direction. That negative is built into that equation. So because, so what we said is that Helga was going to the right, because that's positive. So we could either say that Sven is going negative 1.57 meters per second, or we could say it's 1.57 meters per second to the left. So either one. So that is an example of a recoil problem. And again, we were able to do this little shortcut because they had an initial velocity of 0. So there are some problems with momentum. So hopefully you can conceptually and mathematically understand what momentum is. And then understand that during a collision, momentum is conserved and we could solve for different variables, whether or not the objects collide and bounce apart, whether they collide and stick together, or whether they're together and then break apart. So several different ways that we can solve these problems. And of course, we will practice more of these problems when I see you in class the next time.